All right, so we've spent the past two sections talking about these matrix things, and I'm not sure. I've tried to give some examples where, it justifies why you might want to use them, but it's not an unreasonable position to be like, okay, what does this have to do with any of the, application type stuff we've looked at before? As it turns out, matrices are actually a super handy way to help us resolve systems of equations. Now, you may be thinking, wait, Professor Carroll, we saw systems of equations back in chapter 1, and we didn't need this matrix stuff then. Technically, you don't need the matrix stuff, but it's really going to make our lives easier, as hopefully you'll end up seeing as this goes on. So I've got an example system written up here. So we've got three variables, x1, x2, and x3. I'm sorry, it's not like an XYZ format. All the others will be. So we have these three equations with these three variables. 3x1 plus 2x2 minus x3 equals 3. x1 minus x2 plus 2x3 equals 4. And then 2x1 plus 3x2 minus x3 equals 3. All right. Now, our plan for solving this particular system of equations basically is going to run like that elimination method that we saw for solving a system back in chapter 1. It's just now we've got more variables floating around. So it's a bit trickier in terms of trying to figure out how to combine everything in order to, eliminate, variables and get stuff down where you can work out solutions. So as it turns out, the notes file spells out, we can basically perform operations where we sort of, work our way through combining, these equations in different ways. The catch is, we don't actually need the entire equations because all the heavy lifting is being done by the coefficients of the variables. The variables themselves, they just kind of sit there, and then stuff happens on the right-hand sides of the equations as well. So what we're going to do, rather than writing down a whole bunch of x1, x2, x3s over and over again that are just kind of holding places, let's denote where they are and build a matrix that contains all the numbers we're needing to do stuff with. So what I'm going to do is peel out the coefficients of my variables in each equation and just build a matrix with those. So 3, 2, negative 1, 1, negative 1, 2, 2, 3, negative 1. And we generally will sort of attach onto this matrix the stuff on the right-hand side. That's what we call an augmented matrix. So we've kind of stuck the other stuff onto it. I generally denote an augmented matrix with like a vertical bar separating stuff. It's not strictly necessary, but it sort of helps me mentally keep track of what's what. You may find it useful. I've had some students who will do this that find it useful sort of to put like a little header over top of the matrix, so you remember which column corresponds to which variable. That can come in particularly handy. So the notes lay out a very methodical step-by-step process you can use sort of to attack this thing. The whole method is referred to as Gauss-Jordan elimination. So that's a thing you can do. The basic objective is to perform these operations that won't materially change anything to get this down into what we call reduced row echelon form. So if you get into that reduced row echelon form, it's going to look something like this. So for now, rather than doing all these steps by hand, this is definitely a situation where I would say let your fingers do the walking, let the technology work for you instead of pounding this out. Anyway, so I'll follow up in a video on how we can do this using our graphing calculators, so yeah, keep an eye out for that. But by the time it's all said and done, reduced row echelon form should look like this. We basically, if you remember from the last section, it's kind of like we're generating an identity matrix here. We've got ones ideally running down the diagonal, zeros everywhere else we can get them. Now, this one happens to play out, so when we pull this off, we end up with a column of non-zero values over on the other side. Again, I promise we'll see how this ends up working out momentarily, but just take it for granted. Just trust me for now. I hate saying that as a teacher, but I promise, trust me, this will end up following out. So if we follow back to those labels, we've got that right there. Now, what if we were to translate these rows of this matrix back into equations? Because remember, that's exactly what these were in the first place. We just weren't writing all the extra stuff. So if we look at this first row here, 1 times x1, we normally wouldn't write 1 times, we would just write x1, plus 0 times x2, we normally wouldn't write that, it's just 0, right? Plus 0 times x3, all right, equals 1. So it turns out this first row is spelling out precisely what our variable, x1 has to be in order to satisfy all these equations. Similarly, 0x1 plus 1x2 plus 0x3 equals 1. So as it turns out, x1 and x2 both need to equal 1. Similarly, 0x1 plus 0x2 plus 1 times x3 equals 2. And you can check, if you take these values and plug them back into those original equations, each one of them works for this given set of values. So awesome. We have come up with a solution to this system of equations without having to do a lot of complicated multi-layered substitutions or necessarily pounding through an awful lot of by-hand elimination steps. Again, the technology really assists you on this. I would not recommend trying to do this by hand. For what it's worth, just to give you a bit of a frame of reference, that was what I got when I did this by hand, and I still skipped some steps. So, yeah, it's not the sort of thing I would generally expect you to be trying to work out by hand. Okay? All right. We'll take a look at how the calculator process follows in another video. But I wanted to take a look at a couple more of these examples. And then, we'll discuss what it ends up meaning in this case. So the next example up, like I said, it's back to x's, y's, and z's. But let's see, minus 3z equals 9, 15x plus 5y equals 4, 2x minus y plus z equals 2. Okay, so this is the next example in our notes file. So if we follow along with that same process from before, extract the coefficients, make a big matrix out of them. So we have 3, 6, -3. I'll go ahead and draw in the vertical bar, and then the 9 on the right-hand side. We have 15x, 5y. Note there is not a z term in the second equation. If that happens, you've probably already guessed this, but just in case, we fill it in with a 0. Don't just kind of write a 4 into that spot. That should be a 0. There is no z term. Okay, 2, -1, 1, 2. All right, so there is our augmented matrix for this system. All right, now, again, I'm going to show you how, in a follow-up video to this, how we would actually execute this, getting it into reducer or echelon form, I promise. You'll see it, it's elegant, and it really saves us time. But when I work this bad boy out, I end up getting something a little bit different. So, let's see. So this time I've got some decimals hovering around in here, and that might give me some pause for concern. And then the right-hand column, this time around I've got a couple of zeros here and a 1 down in the bottom. Now remember, these things represented x, y, and z coefficients, right? So now you can write out the types of equations that these things end up generating for you, and that's perfectly fine. The one I want to focus in on, though, is this very bottom row in this bad boy. So we have 0x plus 0y plus 0z. If all of our coefficients are 0, that's just going to be 0, right? The entire left-hand side is simply 0. But over here on the right, we have 1. So that last equation, when we work through it, it tells us that 0 has to equal 1 in order for us to find a solution to this system. There should be some warning alarms going off at this point because 0 and 1 are not in fact equal to each other. This is never true, right? I could technically come up with some circumstance where by redefining equal, but yeah, no, in no context we normally deal with in Math 210 is this equation accurate. If you get something like this where the equation turns out to be just straight up nonsense, then the system, as it turns out, does not have a solution. We cannot find x, y, and z values that satisfy all three of those equations at once. The fancy math lingo for this is an inconsistent system. So that's, that can come up from time to time. Now, as it turns out, there's one more example I want to take a look at here really quickly. So this last example here, we have x minus 2y plus 9z equals 12. 2x minus y plus 3z equals 18. And then x plus y minus z equals 6. All right, so this, when we do the conversion, again, we just rip out the coefficients, 1, -2, 9, and 12 over there. 2, -1, 3, 18, 1, 1, -1, 6. Okay, so there's our augmented matrix. We hit this thing to get it into reduced row echelon form, and this is what happens. All right, so we get 1, some zeros. That's promising, I guess. 0, 1, 0. Looks kind of like that identity matrix from before, and then it all falls apart right here. So, yeah, so that's what our reduced row echelon form for this guy would end up looking like. Now, this time around, that last equation, it doesn't say 0 equals 1. It says 0 equals 0, which is perfectly fine. 0 is, in fact, equal to 0, right? So what's ending up happening in this case is we have what's called, pardon me, we have what's called a free variable here. So this particular system, if this kind of thing happens where you have rows of all zeros at the bottom and none of those like blatantly wrong equations, this system actually has a whole bunch of solutions. It actually has an infinite number of solutions, as it turns out. In this case, based on the way these equations work out, if you rewrite it, you can pick a value for z, and at that point you have nailed down x and y, but z could technically be anything. So you actually have an infinite number of solutions in this case, and those are really your only options. One and only one solution, like the first guy, no solutions like the second, or an infinitude of solutions like this. All right, so that's, leading into this, you're probably at this point really desirous to see what's the magical trick that actually enables us to do this. What's the calculator button that gives us the answer? I will tell you where that button is and how to execute it next time.